With our functions of more than one variable, we will want to talk about rates of change, particularly instantaneous rates of change, which you know by another name, derivatives. However, when we have a function of two variables, like the one I've got generically written on the board, the domain is some subset of the xy plane. Now I'm drawing the xy plane like this because we're in 3D. You plug in an x value and a corresponding y value. That gives you an x and a y point in the plane. You plug it into the function, out pops a z, so you're at a point x, comma, y, comma, z. And if I'm standing on the surface that's defined by z equals f of xy, then what I'd like to know is if I take a tiny step in any direction, will my height increase? Will my height decrease? Now I want you to think carefully. When I'm in 3D and I'm standing at a point, whether it's at home, in the yard, in a park, on Salem campus, I can walk in infinitely many directions, okay? I can choose to walk in the x direction, or I can choose to walk in the y direction. Notice both of those steps I just took were positive x direction, positive y direction. But I could decide to walk another direction. I could decide to walk some other direction. So these partial derivatives aren't the only derivatives we're going to have in 3D. In fact, there are infinitely many different derivatives in 3D. If that frightens you, don't worry. We'll be able to get there from here. So we take it in stages. And our first stage is to define what we call the partial derivative of the function with respect to x. Now sometimes I'll denote that with the name of the function subscripted with an x. Sometimes, because I'm wanting to emphasize that I'm talking about change in the function with respect to x, I'll use some notation similar to what you might have used back in Calc 1. Instead of dy dx, I'm using these strange little curly D-shaped things to represent a partial derivative. It's not all the change in my function that I will experience when I take a step. It's only the change in the height of the function that is affected because I changed x. So I'm standing on the surface of a function and I take a, again, I'm standing on the surface of the function and I take a tiny step in the x direction. So I'm standing at a surface, little hop in just the x direction. That means I did not change y. I only walked in the x direction, only in the positive x direction. I did not change my y value. My y value remained constant, and I hopped a little bit forward in the x direction. And I want to see, did my height go up? Did my height go down? Did my height stay the same? So I have something that looks very much like the definition of the derivative from way back in Calc 1, but you'll notice that y here has nothing to do with my limit. The only place where my limit impacts what's going on inside this new version of the difference quotient is right here at the delta x's. And the only thing that's changing is my x value. My y value is being held constant. And I'm taking a step, tiny little step, in the x direction. And I want to see what is my change in height. So if you look back at the topographical map that I showed you, or you look at that weather map that I showed you, taking a step in the positive x direction on those maps, because they were 2D maps, would be taking a step to the east, to the right. So when I asked you to look at it, pick some points, tell me what was going on. So imagine picking one of those points on either the topographical map or the weather map that I showed you, and imagine moving a little bit to the east. When I do pull this into 3D, my x-axis is pointing this way, so it's a tiny little step forward. I hold y constant. My y value doesn't change, and I refer to that as the partial derivative of my function with respect to x. I'll either denote it by the name of the function with a subscript, or I'll use this notation that's similar to the Leibniz notation. Now, I may want to see what happens if I change y. Take a little step in the positive y direction. Now, again, on those maps that I showed you, those were flat. So a positive y step would be taking a step to the north. But when I'm in 3D, positive y direction is a little step to the right. In that case, I'm not changing my x value when I move. I'm only changing my y value. So x does not change, y does. Y changes a little bit because I'm just doing a little hop. And again, I want to see if my height, my z value, goes up, goes down, or stays the same. I call that the first partial with respect to y. And again, I might use alternate notation. To represent partial of f with respect to y, and that's the way I'd read it, partial of f with respect to y, whether I wrote it this way or that way. Now, of course, these limits have to exist in order for me to be able to talk about these partial derivatives. And when those limits do exist, then I can talk about increasing, decreasing, or constant in the same ways that I talked about increasing, decreasing, and constant in Calculus 1. It's just now I have more than one direction in which I can move, right? So, first, partial derivatives. Partial with respect to x. Take a little step in the x direction. My body's not moving in the x direction. My body is uncovering the board. Change x, hold y constant. That's the partial with respect to x. The partial with respect to y. Change y a little bit, hold x constant. Now you might be wondering what kinds of scenarios could cause my limit to not exist. Same kinds of scenarios from Calculus 1. A three-dimensional hole to fall into, a three-dimensional hole to fall up into, cliffs, breaks in my three-dimensional surface, same sort of scenarios as before. Ready for an example or two? They're not hard to do. Just keep in mind how I said it. Partial with respect to x, you change x, you hold y constant. Partial with respect to y, you change y, but you hold x constant. So let's see what happens when we actually do some of these partial derivatives. All right, so I got a function up here for you, and I want to find the partial with respect to x and the partial with respect to y. To find the partial with respect to x, geometrically, physically, what I'm doing is I'm taking a tiny little step in the x direction and I'm holding y constant, which means if I can take the derivatives using Calc 1 techniques of all the things that have the x's in them, y is going to get treated as a constant. A constant. Y is going to get treated like a constant. So when I look at this part, I see a 4, which is already a constant, and I see a y, which when x changes and y does not, y gets treated like a constant. So there's really this constant in front of x squared. And what's the derivative of x squared? 2x. I'm changing x, but I'm holding y constant. Now 3 is a constant, sine is a function, but y right now, because I'm doing the partial with respect to x, y is a constant. Or I'm treating it like one. I'm not changing y. I'm only changing x. Y is staying the same. Well, hold up then. That's a number times sine of a number. So that's a number times a number, which is a number. And the derivative of a number is 0. All right, my variable is x because I'm looking at the partial with respect to x. So the derivative of e raised to a power is the derivative of the power times e to the same power. And I don't get to put a 0 up here this time because I am changing x, and my exponent is 2x, and the derivative of 2x with x as my variable is just 2. So cleaning this up, I have 8xy minus 2 e to the x. 8xy minus 2 e to the x. Now what if I decided to hold x constant and change my y just a little bit? Hold x constant. That means 4, which is already a number, and x squared is going to be treated like a number because I'm not changing x. I'm only changing y. This is a partial derivative. I am partially looking at my change in z. I am not looking at what x does to the change in my height. I am only looking at what a change in a y value will do to my height. So x gets treated like a constant, 4x squared gets treated like a constant, the derivative of a constant and the derivative of a constant times y, when I'm treating y as my variable, is just the constant times 1 if you need to write it. Oh, now, y is currently my variable. There should not be an equal sign there. Y is currently my variable. So this is sine of a variable. and there's a 3 in front, it stays in front, and the derivative of sine is cosine, and the derivative of y with respect to y is 1, so the chain rule does not add anything to what I've got. Now down on the end, I don't see any y's. I see e to the 2x, and x is being held constant. X is being held constant. X is not changing. X is getting treated like a number. E's a number, 2's a number. X is being treated like a number. 2 times a number is a number. A number raised to the power of a number is a number. This is going to get treated like a number. And so I just end up with 4x squared plus 3 cosine of y. Now, what if I wanted to look at what happens at a particular spot when x is 0 and y is pi? X is 0 and y is pi. And I want to look at the partial with respect to x at that particular spot. Well, if x is 0 and y is pi, plug in 0 for x, pi for y, and I just end up with minus 2. So what does that minus 2 tell me? It is coming from a derivative. So if I am standing on the point on the surface where my x value is 0 and my y value is pi, I'm over here somewhere, standing on the surface, whatever z is equal to, and I take a tiny step in the x direction, will I go up, will I go down, or will I stay constant? Will I be walking flat? Well, the derivative is negative. So that tells me whenever I'm standing at the point on the surface where x is 0 and y is pi, if I take a tiny step in the x direction, I'll drop. What about if I'm standing at that same point and I choose to walk in the y direction, the positive y direction? Well, 0 for x, pi for y. I end up with 3 times negative 1, which is negative 3. So again, I'm standing at the point where x is 0, y is pi, z is whatever it is, and I decide to walk just a little step in the positive y direction. Will I go up? Will I go down? Or will I stay flat? It's a negative derivative. I'll drop a little bit. Actually, which direction would I rather walk in? Being as clumsy as I am, I think I'd rather walk in the x direction. Why? It's less steep. The drop in the x direction is a drop of roughly 2 units. The drop in the y direction is a drop of roughly 3 units. Yeah, I can handle that drop better than the big drop. With a tiny step, ouch, it could hurt. Our interpretations of partial derivatives are exactly the same as they were in Calc 1. We just have to remember and maintain our focus on the fact that our domain is the xy plane now when we're working in 3D. And what we get out when we plug stuff in are z values. And so we're actually looking at 3-dimensional surfaces. But when I work with partials, I either only take a step in the x direction or a step in the y direction, when those are the only 2 variables I got. You ready for some other partials? Let's do it. I may get you all turned around and twisted. These are second partials, second derivatives. Oh man, since I've got infinitely many different directions that I can walk in 3D, I have got so many different second derivatives I could take. Fortunately, we typically only focus on 4 of them. And even more fortunately, because we're in Calc 3 and not a real analysis course, 2 of them very often turn out to be exactly the same. The second partial of a function with respect to x is the derivative of the partial with respect to x with respect to x. So you find the derivative with respect to x, and then you find the derivative of that with respect to x again. That's called a second partial with respect to x. I could denote it with the name of the function subscripted with 2 x's to let you know I'm doing the derivative with respect to x and then the derivative with respect to x again, which means I did the derivative with respect to x, and I'm going to find the derivative of that with respect to x again. And then the Leibniz style notation for that is to use those backward d's and to use a very similar kind of setup that we used in Calculus 1 when we used Leibniz notation. And if you want to read that as d2f dx squared, that's fine. Just remember it's the partial. And so actually when I look at that, I don't even read the letters. I just say the second partial with respect to x, because that's what it is. The second partial with respect to y, you take the derivative of your function with respect to y, holding x constant, and then you take the derivative of that with respect to y. So again, the similar Leibniz notation for the second partial with respect to y looks very much like the notation you used for Leibniz notation for second derivatives in Calc 1. But again, I would read that as second partial with respect to y. Oh goody, I have mixed partials now. And there they are. Why would I do a mixed partial? Well, I'm not sure I can give you a good reason yet for finding a mixed partial. I'll try to think of one while I'm talking. So when I write f sub x, then a y, I'm telling you that I took the derivative with respect to x first. I took the derivative with respect to x first, then followed it with the derivative with respect to y. So the Leibniz style notation, the x's and the y's look flippy-flopped when you look down there at the Leibniz notation. So it's the second partial of f with respect to x first, then y. You go from right to left when you use that notation. You go from left to right when you use this one. A little twisted up, but notation can do that to you. This is another mixed partial. Derivative with respect to y first, followed by the derivative with respect to x. Take the derivative with respect to y, hold x constant. Then hold y constant, take the derivative with respect to x. Derivative with respect to y, followed by the derivative with respect to x, gives me that d2f over dx looking thing, dy looking thing. Okay, again, we read that from right to left when we use that notation, left to right when we use this subscript notation. Partial derivatives. You have some work ahead of you.